Welcome to the fourth virtual conference call with Matthias Hagen today. Matthias Hagen joined what was LTB and now Dürr in 1988. Since then, he has held several engineering and commercial roles and currently has responsibility for sales in Europe, the Middle East and Africa. So please, Matthias, the floor is yours.
Thank you for the invitation. Just let me start with my presentation. Here we go. So this should work now. And I hope that you could see my screen now. So welcome to today's webinar about the possibilities to reduce NOx emissions in glass industry. I'd like to give you a brief overview on different issues, especially on the NOx treatment. So I will give you a short introduction about who we are, who Dürr is, where does NOx come from. So I think it's important to know the background and not just to work on the tail end to treat it. What about limits? How do these develop? Where are we currently? Where do we go? Which possibilities do we have for the NOx reduction? And I want to point out the SNCR, the SCR, and also catalytic candle filters. Then I would like to draw your attention to the possible reactants, give you an information about the reactions which could be used, the differences of the reactants, and also about storage and handling of these. Then finally, I would like to show you some references just to have a better feeling and to talk about the possibilities finally of heat recovery, because I think currently CO2 is in discussion everywhere and everyone wants to reduce his CO2 footprint. And so heat recovery, and especially in the production of electricity, is an ongoing issue and is related also to the NOx treatment. So if someone is wondering what he sees on this picture, so it's not a NOx treatment. It's an arc made of glass, and you can see it that it's in a wooden hand, and it's located on an altitude of about 1,000 meters above sea level in the Bavarian woods, and should be a reminder of the past, that in the Bavarian woods, so in the middle of Germany or close to Czech Republic, this has been a center of glass production in the past. So company Dürr is a worldwide provider of air pollution control technology, and for the glass industry we concentrate on three main areas. So we have on the one hand the flue gas treatment of furnaces, means that we supply SCR, so selective catalytic reduction, the CCF, the catalytic candle filters, and also the ORC technology for electricity production. This is the flue gas treatment. Then we also take care of coating of flat glass, and you have CVD coating, or you have mirror coating, we do the air pollution control equipment for this, and also for, let's say, dedusting applications where you need a VESP. This is also part of our product portfolio. On the right hand, another nice glass example. So if you want to give this as a task to your colleague, you can ask the question, how many glasses are used to build this pyramid, which is about 8 meters high, located in Zwiesel, also Germany, Bavarian Woods. And they have used about nearly 100,000 glasses to build this pyramid. It's very nice. So if you have the chance to visit, go there and have a look. I'm sorry, I catch the cold, so my voice is not the best. If we come down to NOx, what is this NOx about? Where does it come from? So basically, NOx is created in any thermal process. And the main issues are that you have a temperature of above 1000 degrees Celsius, and you have also air to convert the nitrogen which you have in air and oxidize it to NOx. So this happens in any thermal process where you have these high temperatures. A second source could be if you want to clear your glass and you add to your batch any potash nitrate or sodium nitrate. This will lead also to NOx emissions, which more or less could not be influenced so much. So when we now come, why do we want to treat NOx? This is always depending on legal limits, and currently we see that NOx is a more and more interesting issue, especially for glass industry. And if you look into Europe, there we have a European legislation already established in 2013, so nearly 10 years old, but it's step by step coming up in every country that you have to reach lower values, depends where you come from. So in most of the countries you have currently a limit which is about 800 milligrams per normal meters cube, always related to 8% oxygen, because otherwise it would be easy to reach any value if you add some dilution air. So this is limited to the 8%. Or we see in some countries already stricter values of around 500 milligrams. If you compare these values to other industries, I would say that glass industry is in a very comfortable situation, because in other industries there are currently values of 200 or 100 valid. This we can see in Europe, in glass industry not now, but if we go to China, which usually European people think, yeah, in China they have quite high emission values, not a problem to build a plant there. No, that's totally the contrary is right. They claim for values of 100 or 200 milligrams. So China is, I would say, the front runner in terms of emission reduction for NOx. In Europe, usually if these values are applicable, you have a kind of a grandfather rule, which means that if you run your current glass furnace, you can run it with the current values, but if you make a major repair or exchange the furnace, then the new values will apply. A different issue is if you have, usually people think if we shift towards oxy-fuel, then we don't have any more burners with combustion air, so NOx will be not more a problem. That's only part of the truth, I would say. For sure, you will reduce your NOx emissions, but also for NOx in oxy-fuel, I know many cases where a NOx treatment has been required due to the fact that you have a limit which is not in milligrams per nanometers cube, but in kilograms per ton of melted glass. And this you can then calculate yourself quite easily what this means, but there is still, I would say, a challenging value you need to reach. So if you add some nitrogen containing things to your glass to clean it, for sure you will have to do anything. If not, I would say it depends on the furnace. As we are now at SGT, I also put a few into the UK, and there we expect in 2026 stricter values. So this depends on the single permission which you have from the authorities. So we already see some upcoming projects in glass industry there due to this fact. So what happens, just from a chemical standpoint, the NOx which has been created, you could not suck it in with a NOx vacuum cleaner or things like that. This we could not offer, unfortunately. So what we can do is we can create or force a chemical reaction of the NOx, and this is more or less a reduction. So we are offering some reactant to take out, if you look at the first line here, to take out the O from the NO, to take that out and to combine this with another stuff, and to just give me a second, and then to create a pure nitrogen from that. So this is, in chemical people talk of a reduction. So we take off the O here from the NO and create pure nitrogen. So this is the function we do, and this could be achieved by adding a reactant. And in this case here, you can see in the chemical reaction, it's ammonia, which we add. And basically, we have two types of reactant, ammonia or urea. Urea is better known currently as AdBlue, which you have for your car to reduce the NOx. But I come to that later on when you look on the formula and how this behaves. So to make this reaction work, we need either above 900, so around 950. This would work, this reaction, or we use a catalyst which would enable us that this reaction would take place at a lower temperature. So the catalyst we are talking about is only the reason to reduce the temperature where this reaction happens. No other function. So to summarize, we have more or less two possibilities. If we want to get rid of this NOx, we could either optimize the furnace or the firing in the furnace to reduce the temperature of the flame and to make soft flame, is that this would increase the CO, which we do not want, because sometimes you have already CO limits, most times not, but CO is more or less a fuel, and if we have CO emissions, we spoil them fuel into the flue gas, and no one wants to do so. So we want to have an energy efficient furnace, so this does not make sense to do so. But if we have a proper furnace design and a proper burner design, values of around 800 milligrams could be achieved without creating additional CO problems. The alternative is that we take care of the flue gases and we do a tail end solution. We could add a system there, which means that we could optimize the furnace in terms of energy and do not care about the NOx in the furnace. And for the NOx, we take care in the flue gas with a flue gas treatment system there. So what are now the possibilities in a flue gas treatment? Basically, there are three possibilities we have. We have on the left-hand side, we have the SNCR, selective non-catalytic reduction. Non-catalytic means that there is no catalyst involved, and it's purely the reaction we talked 2 slides previously. So it's a pure injection of ammonia into a hot flue gas stream. The alternative is on the right-hand side, the SCR. So we use a catalyst to run this process at a lower temperature, which we usually have in the flue gas. Or in the middle, the solution to use a catalytic candle filter who combines this catalytic reduction with a dedusting and also treatment of sour components. We now look into these three systems a bit more in detail. I think that's useful to understand what's happened there. So the classical SNCR, it's quite easy. You just inject ammonia water into flue gas, but you need to have certain conditions that the reaction will take place. On the one hand, you need a temperature between 950 and 1000 degrees C. And this you have in a glass furnace only in certain areas or under certain conditions. So, but not only in glass, it's in general difficult to have this temperature window in a certain area. And in this area, you then should install your nozzle to inject it. So if you inject it here and you have the temperature up front, and here you have 50 degrees less, then the reaction will not take place and nothing will happen. So it's very much depending on the temperature to find the right spot where to install the nozzle. And even then, the reactivity and the fitting point is difficult. So what we see in some cases that we can reach efficiencies of about 60% reduction efficiencies, so not more. On the negative side, we could also see that due to the injection, and I would say more or less uncontrolled injection of the reducing agent, not 100% of the agent is used. So we will have additional ammonia on the outlet of our system on the stack, which causes additional problems, because ammonia, I would say, is even worse than NOx, and authorities also put some limits on that. And for sure, if you get a new permission where NOx is controlled, they will also claim for some ammonia slip to limit it and to avoid that you just add ammonia like hell, and NOx will be perhaps reduced, but you increase the emissions of ammonia. Both NOx and ammonia are containing nitrogen, and this is more or less a fertilizer. So the authorities also want to avoid that this fertilizer will come into the surrounding of your factory. You can say, no, that's good, then things start to grow, but believe me, that's on the long term, it's not a good way to have these deposits of ammonia then surrounding your factory. So then the alternative would be then the selective catalytic reduction, where at remarkable lower temperatures, which are typical for flue gases in glass industry. So we do not need to reheat it or to adjust the temperature so much. We could right away use the catalyst and it will work perfectly. We could reach efficiencies of about 90 to 95%. So quite high, and for sure sufficient for the values you have to achieve. Such a catalyst is a ceramic grid with very fine channels, which just 2-3 millimeters channels. So dust could be could stay in these channels and on the long term clog our catalyst, which would reduce the efficiency. You have to exchange the catalyst on a regular basis, and to avoid that, sometimes it could be required to have additional soup blowers, which then have also an additional consumption of compressed air. So it depends on the application. In any way, that such an SCR should be installed after a dedusting. If you would use it upstream with dedusting, the lifetime, you would not be able to celebrate first birthday. So the lifetime would be quite short. So you need a dedusting anyway. For bankhouse filters, just to keep that in mind, you need to reduce the flue gas temperature for the baghouse, for the bags, down to usually, let's say, for sure below 250, which would then be for SCR not the fitting temperature. So there it could be required to have a reheating, which would require then additional energy, and so the whole installation is perhaps not the best choice. So when we now talk about the typical catalyst, this is one of the first questions which pops up. How long does it last? So if we could exclude the problem with the dust, we could say that a catalyst will live, I would say, between 5 and 10 years. So something like that. What you can see here was have been two curves which we have measured. The dark blue one shows a catalytic, in that case a candle filter, but the catalyst is the same than the SCR catalyst in a new condition. So you see efficiencies of more than 90% over a long period of time, and also over a high spread of temperatures. So if we are in the window between 300 and 400 degrees, to reach 90% is not a problem at all. The light blue line shows the aging, and this was made after 35,000 hours. So roughly about after 5 years. So then you can see a decrease of 1 or 2% of efficiency, but more or less it stays the same, and even then 90% could be reached without a problem. So now the third possibility we have is the catalytic candle filter, which has some candles inside, which are also coated with a catalyst. So we have a similar procedure. We install it in the flue gas. We have to add some urea, but also, as we want to get rid also of other pollutants, we inject some dry sorbent as well. The efficiencies are similar to SCR, and also the temperature range. The big advantage of such a solution is that we could reach quite low dust loads in the clean gas, which allow us to install heat exchangers here without big efforts for cleaning. So this is the big advantage. So when we look into that, how does it look like in detail? You see on the right corner here, you see a RAM picture, which was taken with an electronic microscope. You can see the fibers, which are part of the candle, and you can see also these small rectangular plates here. And these plates, this is a catalyst, which is on the surface of the fibers. So if the flue gases have to go through this candle, they hit the catalyst directly, which gives us an advantage compared to a classical SCR, where the catalyst is in, I would say, caves, and it takes some time until the flue gases move into these caves. So here we have a direct reaction with the catalyst, so quite fast, and we have no limitations due to the so-called diffusion, which we have in a classical SCR catalyst. Also, any dust could not create a problem because we take away the dust on the surface, on the outside of these candles, so, and it could not clog it. So the function will stay over a long period of time. So the whole function of our filter I could show you in a small film. So we could see the application. You have the glass furnace, you have the CCF filter, and perhaps downstream energy usage. And the filter has the two injection points. On the one hand of the reactant for the NOx, on the other hand the dry absorbent. And if we look inside, we can see the single filter candle. So we can see NOxes coming together with the reactant, urea. Other pollutants are coming like SOx. And of course, with the dry absorbent, which is typically hydrated lime, and of course also dust from the furnace. So the NOx will react inside of the filter on the catalyst and be reduced. The SOx will react on the outside with a hydrated lime to calcium sulfate, and this will stay on the surface of the candles, and the same would apply for HCl and HF, all sour components. All these pollutants will get into the hopper and will be discharged, and the clean gas could then leave the filter, and we could install a heat recovery without a problem before we are entering the stack. So, when we now, I'm sorry, when we now compare all these solutions, and more or less we have the solution for a glass furnace always related to the let's say to the oldest treatment method of flue gases, to all the dusting. So it could be either that you have an existing electrostatic precipitator, or you have an existing fabric filter and you want to add a NOx treatment. So for the fabric filter, you can add an SCR catalyst, but for this you need to make a reheating, so you need to add additional energy. For the electrostatic precipitator, it's possible to add the SCR system without any problem. I would recommend such a solution for all systems where the electrostatic precipitator is not too old, in a good condition, and gives us reasonable clean gas values for dust. If that is not the case, I would think of a new system, and the preferred solution would be a combination with a CCF, where you could treat all the pollutants in a one-stop shop. So quite easy in one single stage. When you now compare the systems, it's difficult to give you a recommendation and to use the values or the conditions you want to look at. The CCF solution is for sure, compared to the others, one of the smallest. It gives you extremely low dust emissions, and this is an issue which I would like to point out if you go into the future, because in the future PM10 and PM2.5 will be important issue. So PM10 means particles smaller than 10 microns, and PM2.5 particles smaller than 2.5 microns. These extremely small particles are, I would say, for sure not healthy for mankind. And so currently we see slowly an increasing demand to take care about these. Currently, mainly on the emission side, so people are looking what is the surrounding, which particle load do we have in the air in industrial area. And the next step will be that they will point to industries and say, you have high particle emissions, please take care about these. So with the CCF, this is not a problem, because especially the fine particles will be destructed. So we reach extremely high efficiencies on the small particles. So for the NOx treatment itself, I would say all solutions are comparable. So there is not a big difference. For the lifetime of the catalyst, it depends always on the dust load. So you have a slight disadvantage usually on an electrostatic precipitator, because he has higher dust emissions. And if you then look on the life cycle costs and all the efforts you have, here's just a simple system with one stage. So these costs are quite low. So as promised, I want to go into the reactants. And I'm sure you will be wondering why I show you pictures of chocolate, and it's easy to explain. If you just imagine droplets of ammonia water, and you imagine that these look brown, then what you could see on this picture here is a mass of droplets of ammonia water. And the big difference is when you compare this with urea solution, you can see that here the same droplets more or less are packed into a nice foil, one by one. And this is the big difference. So if you would take a smell on this side, it would be easily detectable. It smells like chocolate. Here it perhaps, but it's not easy to detect. And the same applies for the difference from ammonia to urea. So urea is more or less a packed ammonia. And this is important to keep that in mind. This means when you look at the chemical formula down here, you see here the pure ammonia, you see here the urea is mixed with a little bit of other things, which is the packing. The advantage is that urea does not smell like ammonia. Urea is not harmful than ammonia. And if you inject it into a flue gas, you could imagine that here the chocolate will melt immediately due to the temperature. And here it takes some time. First, the foil will melt or burn, and then the ammonia could melt. So it takes a bit more reaction time if you inject urea compared to ammonia water until this will react with the NOx. In most cases, this difference of reaction time is neglectable, so it's not a problem. But sometimes it could be interesting, especially if we are talking about lower flue gas temperatures, then this could be really interesting. So the bigger differences we have when you talk about the storage. Ammonia water is harmful to water, to drinking water. Sorry. So you have to take care where to install a storage tank. If it's an area where you create drinking water, this could be a problem, and you have to take special measures for the storage. For sure, you have to avoid that the ammonia will get into the drinking water. For urea, it's a bit more easy. But if you compare then also some other issues like freezing point, so you could imagine minus 47 degrees C. If you store ammonia water outside, this won't be a problem at all, because you would never, except Russia, you would never reach so low temperatures. For urea, it's a bit different. So you have 0 degrees, means you need to heat the storage tank or to put it inside. From the price level, the ammonia solution is the cheaper. So urea is a bit more expensive, but one advantage is also available in IBC, so industrial bulk containers, which can take about 1 cubic meter. So it could be also for smaller applications and for smaller demand on reactant, the preferred solution, because we then could store the urea inside. Ammonia is not allowed to store inside. So this could be an advantage. what we see is that especially for smaller furnaces, urea solution is the preferred one, whilst for bigger furnaces or for several furnaces, ammonia water would be the preferred solution. So to give you an idea, what do I have to expect in terms of consumption? How much do I need from this stuff? Let me use a typical example. If we would say you have, let's say, 250 tons per day furnace, it will have around 30,000 normal meters cubed, so in between here, of flue gas volume, and we have, let's say, a proper furnace where we have emissions of, let's say, 1,000 milligrams, and we have to go down to 500. So we would have to reduce it by 500, so we can use the blue line. So go up here to the blue line, and then we see that we have consumption of, let's say 20-25 kilos per hour of ammonia water. So if you now would ask, how much would that be in urea solution? Of course, as we have the packing, urea has a bigger volume, so we would have to add a bit more, but the usual commercial available product concentration is a bit different. For ammonia water, you use normally 24.99%, so below 25, because if you exceed the 25, then additional safety measures would apply and no one wants to do so. So you stay below 25. For urea, you could use higher concentrations, and the typical concentration is 40%. So if you compare these two, the consumption and the amount you need would be roughly the same, so also around 25 kilos of urea. So this should give you a feeling on the requirements, but please calculate in a good way. 25 kilos per hour. The day has 24 hours, so you reach quite fast bigger numbers, and then you can calculate how often you would have to exchange a 1,000 kilogram IBC or a 40 cubic meter tank. So I think that's easy to calculate yourself. So how does the storage look like? So I've shown you some examples of ammonia storage, because urea storage is a bit more simple. So usually the tank is located outside due to the risk of the ammonia. It's a double wall tank. So in case of any leakage, the leakage could be indicated and also collected. We have some filling stations, because you get it supplied by a truck. So he needs a pump to fill the tank. Of course, also a pump for the supply of the system. You need some additional measures. If you fill the tank, just imagine the tank is empty, and you emptied it up down to here, perhaps 1 meter is remaining in here, and then you start filling it with new ammonia. Then the rest of the tank, the air volume inside, will be saturated with ammonia. And if you would just fill the tank and vent it to the outside, the typical ammonia odor would occur, and your neighbors would complain quite fast. To avoid that, we supply a small scrubber which works during this situation and could reduce the ammonia venting to the ambient. When you look at the filling station, you always have to consider that a tank and the pipe from the tank truck could burst, and then ammonia would be spread. So what's considered, you close the valves on the tank, and then the remaining ammonia will be collected here in the concrete in a special area, which is sink in the middle, and you should collect it and then discharge it. So now coming to some examples. A typical SCR example we installed at a plant in Germany, container plant. So you see here, this is the cube of the pure SCR. This is just the ductwork. The system works downstream and ESP. The reason we have decided for this was quite easy. The ESP was not old, in a very good condition, reached a very low dust emissions of less than 5 milligrams. So there was no reason to broke down the ESP and build a new complete system. So we just supplied an SCR system to that. Another example of the same company but different location. There they had an ESP which was 25 years old. So the idea was then not to install just an SCR, but to install a complete new system with a catalytic candle filter. And we take care here of 2 furnaces combined in one filter system with what you can see here, various bypasses and possibilities to get around in case of any failure or problems. Here you can see it, source from 2 furnaces go into the filter. We have here on the clean gas side also connections for a future use of heat. So an ORC or a heat exchanger could be added later on easily. If we go to bigger sizes, especially in flat glass production, we have supplied this system here to Kibing in China. The big difference here was that Chinese regulation required low values for everything, not just for NOx, but also for SOx. And that's the reason for this huge tower here, what you can see. So this is the filter, and this huge tower is just for an optimized sulfur destruction. We have a longer residence time and recirculation installed for the hydrated lime, which enables us to reach extremely low values for the sulfur. Sorry, skip that. Also special glass, which is a very interesting item because borosilicate glass is not easy to handle. You usually have problems with boron oxides, which is a nasty dust which clogs everything. So it would also be a problem for a classical SCR installation. So they selected candle filters where the dust stays outside, and we could not see any problems in clogging of the pure filter bags. So a final view, I want to put your attention on the heat recovery. If we have such a system working, we have here on the outlet a temperature of, let's say, between 300 and 400 degrees, which are ideal for the use of an additional heat recovery. Heat recovery in the glass industry seems sometimes a bit silly because most glass furnaces or glass factories suffer from heat and they want to have more cooling than heat. So just for the showers of the employees, it does not make big sense. But then the important or interesting thing could be to use the heat for creating electricity. And here I have also a slide where you could see or have a rough idea on the amount of energy which you could recover in terms of thermal energy. So if we stay to the same example, we have around 30,000 normal meters cube, and we have perhaps a high temperature of 400 degrees of our flue gases. So we could use a maximum, let's say here, 160 Kelvin of differential temperature. We reach around nearly 2000 kilowatts, or 2 megawatts of thermal energy which we could use. And now if we want to create from this electricity, we should consider that we have an efficiency of only 15 to 18% in an ORC process. So for those who do not know it, ORC means organic Rankine cycle, and more or less it's the simple vice versa process of a fridge. So in a fridge, you add electricity and you get cold. Here you add heat and you get electricity. So that's the simple explanation. If we need to do so, we can do that in an extra lesson. But I think we are running out of time to explain this in detail. But if we stick to the example, we would be able to create roughly about 300 kilowatts of electricity. And I think this would be a remarkable number which you could use in your factory, either for the normal electricity use or for the furnace for the boosting. So this would make sense and would create an advantage for you for the CO2 credits, which you might claim for or have to purchase. One more remark to the ORC process. Even if you create, so you take out the heat here from the flue gas, you run the turbo generator and create the electricity out here, but we need also a lower, or we create a lower calorific value of heat, so usually warm water, which we either have to cool down or we could use. So even if you install an ORC, you would create enough warm water for the showers of your employees. So this could help on top. So I think we've reached the end of my today's presentation. I would like to say thank you for listening. I hope that I was not too boring and you you are able to take some interesting new points home. If you liked it, give a feedback to the Furnace Society. So I give it now back to Nigel or Ian.
Okay, Matthias, thank you for a very interesting presentation. While you've been speaking, we've had a few questions come through the system, so I'll ask on behalf of the attendees. And are the collected constituents reused from the CCF or sent to landfill?
A very good question and a very interesting question. Basically, both is possible. So you could, the easiest way is to put them to landfill. The other possibility is to reuse them in the batch. From our experience, I would say it's done so and so, because for the batch, sometimes if you have a very specific and high quality glass, the customers do not want to have any variations in their glass quality. But you could do so because the main ingredient would be hydrated lime, and this you use in a soda lime glass anyway. So this could be done, and we also supply automatic transport systems that you can get this, this residual waste back into the batch house.
Okay, thank you. Another question is, are there any new technologies that are being developed in the realm of my teeth are falling out, I'm sorry. In the realm of abatement, sorry. Apologies.
Ideal, it's abatement.
Yeah, I've got it. I finally got it out. My jaw wouldn't work properly. Yeah.
Don't worry. So I would say that the last development was the catalytic candle filter. And in terms of NOx treatment, there have been no other developments up to now. I think if we look in general into new developments, the focus would be currently going towards CO2. And we will see perhaps in 5 years, the first industrial usable solutions for CO2. But for NOx, we stick to the current solutions.
Okay, thank you. Another question. How is the hydrated lime added to the CCF for DSOx, and how do you remove the byproduct?
We use it. It will be supplied and stored in a silo, and then injected with a blower into the ductwork of the flue gases, where it will already react during the time it's in the flue gas mixed, but the main reaction takes place on the surface of the candles.
Okay, thanks. And one last question, I think we both can answer this one, is can the presentation be shared to us via email? Yeah, so I guess whoever's asking the question, if they send you an email, you'll forward the presentation.
Yes.
And also the SGT will be uploading this recording onto the SGT website for people to view as well.
Yes.
Okay. Oh, one more question. In terms of the combustion efficiency, is there any reference of new development sun burners to allow for reduced NOx?
We take care of flue gases, and we are not a furnace design or furnace construction company. So this, I would say, should be a question which you should pass to them. I know that what I mentioned, a lower NOx burner to reach perhaps 800 milligrams. This is possible with a modern furnace. But to go further below, I think this is basically not possible, even if you would develop a different type of a burner, because the conditions you run the glass furnace are so that you will create NOx in any way.
Okay, another question now for you. What are the typical ammonia levels, and do you foresee a tightening going forward? And will a scrubber be needed in the future?
Good question. So when we look at our systems, the official limits for ammonia are, I would say, roughly depends on how you negotiate this with your authorities, but the values are between 10 and 30 milligrams, the required values. We reach lower values, and so a scrubber is not and will not be needed in the future.
Okay, so these questions keep coming. Another one. Can CCF candles be exchanged during operation? If so, how?
Yes and no. If it depends on the design of the filter. currently we see that authorities claim for an uninterrupted treatment of the flue gases. Uninterrupted means really availability of 100%. This 100% availability would normally require of a redundant system. So to install 2 filters in parallel. As this no one will do and wants to invest so much money, we found a solution to split the filter into different modules, like you have seen in the one example with the 6 modules. So then what we can do is we can take out one of the 6 modules, make an exchange of the filter candles in this module, and run the furnaces with the remaining 5 modules. So we can separate each of the modules and then make some repair or maintenance.
Okay, and another question. For hydrogen combustion, would the systems, or all the systems to reduce NOx to be, would the systems be the same to reduce NOx with hydrogen combustion?
To be honest, I have not seen any hydrogen system up to now. And I would be eager to see some really values, what they expect to have. But if I would consider that hydrogen is just a different thing compared to methane or any other fuel, the effect of creating NOx will be the same if you use hydrogen. So also the treatment would be the same.
Okay, well, that looks like there's no more questions. So once again, thank you for your time, and thank you for a very interesting presentation, Matthias. And thank you everybody for attending. And to remind you that our final virtual training course will be in a month's time, which will be presented by Jan Teron from Lucidian. And he'll be talking about diffusivity of hydrogen in tin bath blocks. So something completely different.
Yeah,
which is good.